So in this video, what I want to do is to talk about using the technique of integration by parts in such a way that we obtain on the right hand side of a relation the initial integral again. And this can very often let us calculate the initial integral. So let me just try to explain here what the strategy is. So I is going to denote some integral which we're going to try to calculate. We're going to use integration by parts, and quite often one needs to use integration by parts twice, but not always. Having done that, we hope to obtain, in these cases that I'm going to talk about in the video, we say that our initial integral is some stuff, which I'm going to not worry about too much at the moment, plus the initial integral multiplied by some constant. So k here is a constant and I is the initial integral. It is what we started off with. So because we have the same thing on both sides, on the left hand side and on the right hand side, we can bring this over to here and we have our initial integral multiplied by the 1 here minus k, which is whatever this is, and this is going to be equal to whatever we had here. And then we can divide both sides by 1 minus k, that's the coefficient of I here, and we say that our initial integral is 1 over 1 minus k multiplying all of whatever these terms are here. And in some cases this set of dots here may denote some functions, in other words there might be no integrals here at all, or sometimes there is here a simpler integral, and then we have an example of what's called a reduction formula. So let me also point out that the dots may include an integral, and in that case we have a reduction formula. And I have a video about reduction formulae already that you can look at to see. So this is the strategy, and what I'm going to do on the next slide is to look at an example of how, starting from an integral, using integration by parts, we can get some stuff plus the initial integral, we bunch it together, divide by whatever constant we have here, and in that way we can obtain that the initial integral is something which we hope to be simpler. So let's look at the next slide to see some examples of how this can sometimes occur and sometimes be useful to us. So the example that I want to look at on this slide is the integral of the sine of x multiplied by e to the x integrated with respect to x. And when we look at the integrand, we see that it is a product of two factors. There is not a simple relation between them, encouraging us to perhaps use the idea of a simple substitution. So instead we think, let's try integration by parts. And when we do this, what we have to do is to decide which factor we are going to integrate and which factor we are going to differentiate. And actually for this example, it doesn't make any difference. Both routes will lead to the same thing. But let us remember our idea of late, and the word late tells us that this is logarithms, this is algebra, this is trigonometry, and this is exponentials, and it suggests that we should take the first letter to occur in late as the function which we are going to differentiate, and the other function we will integrate. So following that, we decide, since t comes before e in late, that we will differentiate sine of x and we will integrate e to the x. So we're going to say that u, the function we're going to differentiate, is sine of x. V prime, the function which we are going to integrate, is e to the x, and therefore u prime, the derivative, is the cosine of x. And v, the integral of e to the x, is of course just e to the x itself. And the formula that we are going to use is the integration by parts formula that the integral of uv prime with respect to whatever the variable is uv minus the integral of u prime v with respect to the variable. So in our particular case, we have that our integral, is going to be u times v, and that's sine of x times e to the x. So it's sine of x times e to the x minus the integral of u prime, which is cos of x, times v, which is e to the x, integrated with respect to x. And when we look at this, we think to ourselves, perhaps for a moment, that this doesn't seem to be helping at all. But then we think, well, if we were to do it again, perhaps we could get back to the initial integral. Now, there are two ways of doing this. One way would be to use integration by parts again, and now to integrate this factor, which we had previously differentiated, and to differentiate this factor, which we had previously integrated. And if we do that, all we are doing is unravelling what we have done before, going backwards, and we will end up with that I is just equal to the integral of sine of x e to the x with respect to x. So we have the relationship that our initial integral will be equal to the initial integral, and that is true, but it is also useless. So instead, what we want to do is use integration by parts again, and what we have to do is the factor that we obtain through differentiation must be differentiated again. The factor which we obtained through integration must be integrated again. So we use integration by parts again, and the way I like to think of it is to say that we have to sort of stick to our guns. In other words, we have to keep doing what we had done before. So we say, therefore, that u is going to be the cosine of x, so that we will differentiate it again, and u prime is minus the sine of x, and v prime, the factor that we are going to integrate, is e to the x, so we integrate this again, and we have that v is equal to e to the x. And I think it's a nice exercise to check that if you were to swap these two around and differentiate this, and integrate this and differentiate this, that you would just get back to this is equal to itself. But now, we are going to stay doing what we have done before, and in this way we obtain that I, our initial integral, is, and we are using this, so it is the sine of x times e to the x minus, and I'm going to open brackets because the minus sign here multiplies all of this, so this was u, this was v prime. We use integration by parts again, so this is the formula we're using, and u times v that we need first is going to be cos of x, u prime, yes, cos of x times e to the x, so that's cos of x times e to the x, that's the uv, minus the integral of u prime v, and u prime is minus sine of x, and v is e to the x, so u prime v is minus sine of x, so that gives us another minus sign, and makes this one plus sine of x times e to the x integrated with respect to x, close brackets. And at this stage we recognize that this integral here is our initial integral. So we recognize that this is our initial integral. So expanding the brackets and noting that the minus sign multiplies both terms, we obtain that I, our integral, is sine of x times e to the x minus cos of x times e to the x, and then minus I. So now we could take this factor over to here, and we have that twice our initial integral is equal to this minus this. So 2i is sine of x e to the x minus cos of x e to the x. So therefore dividing both sides by 2 will give us our initial integral. And I'll just pause to make a little bit of room. So therefore we conclude that our initial integral, the integral of sine x times e to the x, is equal to 1/2, and there's a common factor of e to the x, so I'll take that out, and it is sine of x times minus the cosine of x, close brackets, all times e to the x, and then there is some arbitrary integration constant. And that is our final result for the integral. So we see that what we did was we used integration by parts. Having used it, we saw we had something very similar to our initial integral, but with a sine replaced by a cosine, and that gave us the idea of using integration by parts again. And I've tried to emphasize that it is very important, if you use integration by parts a second time, that whatever was previously differentiated is differentiated again, whatever was previously integrated is integrated again. And if you do that, we then tidied things up, we recognized our initial integral had occurred, we brought all the initial integral terms over to here, we joined them up, we saw we then had 2 of them, divided both sides by 2, and that gave us our final result, and that result can of course be checked by differentiation. So in other words, if you differentiate the right hand side, if you differentiate this, you should get the initial integrand. So with that, I will stop this video.